എവിടെ നാട്ടിൽ എവിടെയായിരുന്നു?
ഞാനോ?
ആ
എന്റെ ഹരിപ്പാടാണ്
ഹരിപ്പാട്.
വീട്.
ആ
വീടൊക്കെ ഹരിപ്പാടാണ്. പഠിച്ചത് ഞാൻ കാര്യവട്ടം ക്യാമ്പസിലാണ്.
അതെ.
അതിന്റെ PhD ഇവിടെ വിക്രം സാരാഭായ് സ്പേസ്
ആ
സെന്ററിൽ.
സുരേഷ് രാജ് സാർ.
അവിടെ
വീണ എന്റെ സീനിയർ ആയിരുന്നു വീണ ചേച്ചി. പിന്നെ ആക്ച്വലി അതല്ലേ മലയാളം. I am from Kerala only and I did my MSc from Parivattam campus, University of Kerala. You registered there, huh? We all registered our end. Then did my PhD from this VSSC under ISRO JRF fellowship, and then postdoc there itself, and then joined the scientist. Physics, MSc physics background, and I did my work on microwave radiometer. Vrinda is also my junior. Camera. Some relatives are there.
PhD in physics or in remote sensing?
PhD physics. My video is coming.
Yeah. Yeah, you can. Control LHL. So, good morning, all of you. Today's our speaker is Dr. Renju, scientist in Space Physics Laboratory at VSSC, ESSO. So she has done a lot of work on remote sensing using satellite data and ground-based observations, and especially with a focus on microwave remote sensing. So she has many publications, reputed publications. Also, she's a part of nation's moon program, and I invite her to this program. So now you can. Yeah.
So, very good morning to all of you. So, I'm as Unikrishnan introduced, I'm Renju from Space Physics Laboratory, Vikram Sarabhai Space Center. So, my main research area of interest is on microwave remote sensing, where using the radiometric observations to study the lower atmospheric characteristics, boundary layer characteristics, and microwave remote sensing for studying the atmospheric convections, and also the utilization of this microwave remote sensing for surface studies also. So, today my topic of lecture is microwave remote sensing. So, any remote sensing, it is we have to, since it is a basic coursework, we start with the understanding on little bit on the electromagnetic waves and how it propagates through the medium and its interaction with the medium. Okay. So, as we know, all of us know the electromagnetic radiation. Everybody heard about the electromagnetic radiations. So, electromagnetic radiations are the waves where there is electric and magnetic field oscillating in a perpendicular direction, perpendicular to the direction of propagations. So, they are perpendicular to each other. And the wave has the characters, both the particle and as we all studied, wave nature is there. Wave having the electric and magnetic fields perpendicular to each other, and particles, as we know, as in the terms of photons we studied, it has a particular set of energy. This discrete energy will be there, which we know the E equal to h nu formula. So it all depends upon the wavelength and frequency of the waves. So all the characteristics are depending on that. So if we tell the stronger the electromagnetic radiation means, the frequency will be the higher, and the depending upon the depends only on the wavelength and the frequency of this. And in the electromagnetic radiations, we have classifications, as we know, spanning from the gamma ray to radio waves, gamma ray, X-ray, ultraviolet, visible, IR, microwave, and radio. So depending upon the applications which we are studying, these remote sensings are classified based on, particularly we have the IR remote sensing, we know, the microwave remote sensing, if we are dealing with the 0.3 gigahertz to 300 gigahertz regime, if we are taking for remote sensing application, it as microwave remote sensing. It is basically in the centimeters to meter. The wavelength is slightly higher. Wavelength is slightly higher means it has a deeper penetration capability. So the microwave has an advantage over the IR is that it can traverse through the atmosphere even during cloudy conditions. It can give so surface characteristics also we can study it, and even the atmospheric, because some species are sensitive to this microwave remote sensing. So we can see the atmospheric opacity also. So first we understand the waves, then its interaction in the medium, then in the atmosphere, and then how we are using it for the remote sensing application. This will be the outline of the talk. So as we know, all these electromagnetic radiations generated
with some sources are required. It is how the energy transitions between the energy state levels determines the which type of spectrum it would be. So if it is nuclear transmissions and disintegration energy is very high, we say gamma ray transitions will be there. And if it is ionization by inner electrons and all, it will result in the X-ray spectrum. And as it is going, all this we learned in our basic textbooks, but what I want just to refresh it so that you're understanding. So as we know in the IR and all, it is the molecular vibrations and lattice vibrations. Vibration spectroscopy will lead to this one, whereas in the microwave, it is mainly the molecular rotations may be the most thing. So which are the molecules which are sensitive to this molecular vibration transitions are mainly used to study using the microwave remote sensing, whereas we know this polar, non-polar molecules and all we studied. So some molecules are this molecular rotations, transition levels are occurring. So examples are the water vapors and all. So these are all microwave. We can use the remote sensing techniques to study those species. So just to have a glimpse, there's some equations. This is a basic Maxwellian equation where we know how the electric field when interacting with the medium, there would be a propagation constant gamma when it is expressed in the terms of alpha plus I beta, where alpha is the medium's attenuation coefficient, attenuation constant, and beta is its phase constant. So even if any electric field when traverses through a medium, we know that it get attenuated exponentially. That is what the figure is showing. So if we take it at the depth Z or at the depth Z, if an that electric field magnitude is decreases or exponentially decreases by 1 by ETH, we call it as the penetration depth of any electromagnetic wave. So this factor is important. The skin depth we call electromagnetic. So this determines which type of waves we have to use in which type of medium which have the penetration capability. Okay, so this is the one of the reason for choosing which type of waves. If we want to study the surfaces and all, which if we want to deeper subsurface level activities we want to study, means subsurface characteristics we have to study, we have to take a frequency, select a frequency in the remote sensing which should have a penetration much deeper into the surface without much affected by the atmosphere. So there the skin depth plays a significant role. So in the if the equation we take this gamma or the alpha, the gamma what we called is a propagation constant, which is consisting of the attenuation constant alpha. And if we take a perfect dielectric medium, means there would be no conduction in the medium. It is an ideal case. This is a perfect dielectric, which we call lossless medium. There is nothing getting lost by the electromagnetic wave. So if that medium we are taking, the conduction becomes 0. So the delta X become it is the 1 by of terms of the atom. So what happened? The attenuation will not be there. Then the penetration depth will be infinite. Means it won't be get any damping. It won't be get attenuated. It will be infinite. But if you take a perfect good conductor, what would be happening is that alpha become higher because the conduction becomes higher. So these all depend upon the dielectric also of the medium. So these are the equations. If we further divide into minute levels, we will find that this depend upon the epsilon part of the equation, and epsilon is itself we can divide into imaginary and real part. So if we go into deeper into these equations, we find that the dielectric imaginary part will determine the loss factor of a medium. So if we know the real and the imaginary part of this, we can determine the skin depth, how the magnetic waves or electromagnetic can penetrate into a medium. The another factor of the any waves is that the polarization term. So we know the both electric and magnetic fields are there in the waves. So if we take the magnitude of the direction of the electric field alone, we call it as a polarizations of the wave. So polarization also is if we take the locus of all the electric field wave vector as it propagates through the medium, we can call it as based on the shape. If it is linear or straight line through the medium, we call it as a linear polarization. If it follows or it traces a circular motion where every time the electric field, there is amplitude will be the same, but phase changes by the 90°. We get if we trace it, we get a circular polarization. And if it is traces an ellipse, it become a elliptical. So if in the circular polarization itself, if we are going right hand, means counter clockwise, we call it as a right-handed circular polarization. If it is going to left counterclockwise, we call it as left hand. Why all these things? If you take the application, this linear polarizations and all in the satellites or in the radars, if you see it is again classified into horizontal and vertical. If you see from the bottom figures, if the electric field is perpendicular to the VV, is perpendicular to the plane of incidence, we call it as a vertical polarization. If it's horizontal or parallel to the surface, we call it as horizontal. Where the application comes in the radars and all, if you see that the transmitting wave is vertical and receiving in the same polarization, depending upon the which type of characteristics we have to study. If we are sending horizontal and receiving horizontal signals, if we are sending H but receiving opposite, this all determines the speech or the surface studies which we want to study. So in the polarimetric radars and all, we are using these combinations. Then we get, depending upon the backscattering or signals what we get, and the change in the V or in the H will determine the surface characteristics what we are studying. Okay. That is coming in the subsequent slides. So all these are basics of the tools what we are studying in our remote sensing applications. Okay, so these are the design. Then what about this about the linear? So linear, every time the signal should be in a particular orientation. H means sending, V should come, then only we can get the cross polarizations, only we can get the real characteristics we can study. But in this cases of satellite communication, all there is the orientation is highly mismatching maybe occurs. If the transmitter is sending something receiver, and interferences can cause us alignment, that time cross polarization will help, because there the loss factor will be very less, because it will take the signals in all the directions. So RFIDs, means radio frequency interferences devices and all are using circular polarization type of radiations. So depending upon the applications in the remote sensing and which type of characteristics we are studying, actually that is the purpose of all these different type of polarization study. And the another significant this is that the angle of incidence also been selecting. Okay, so we know, we studied in our classes that at the Brewster angle, the vertically polarized, or the what we told horizontal and vertical component, if you are taking, the vertical polarized is totally transmitted into the medium, whereas horizontal part getting reflected. So in the H and V polarizations, when we are using the local incidence angle of that satellite, if you see, will be selected in such a way that the difference should be H and V should be very high. If you see that is coming in the subsequent slides. In some of the satellite missions, if you see, the angles are selected in such a way so that we can have a vertical and horizontal. This discrimination should be high so that the characteristics we can study. So H by V or H minus V, we get the values. So these are the basics for why we are using these angles. Okay. So as we know, when it is interacting the radiations with the medium, so we all first assume it as a black body. For the easy of the approximations and computations and all, we are always assuming it into a black body assumptions. So as we know, the Planck's give the equations to compute the thermal the radiations emitted at particular temperature, and it also depending upon the wavelength or frequency also. So if we see the spectral radiations emitted by the sun and the peaking at the high temperature, we can see that the peak is shifted to the shorter wavelength side. Okay, so as we go, the temperature is decreasing, the peak is shifted to the longer wavelength side. So as we know, the lambda maxes, they are inversely proportional to the temperature of the body what we are studying. So that is that equation what is derived by Wien's displacement law, where the lambda is equated to the 2897 micrometer divided by the temperature of the Kelvin. So this has an implication that whenever we get a radiance spectrum from any sensor, what we can decide the temperature of the body which is emitting it. Sometimes we cannot go, all the satellites is not going and measuring the temperature there. So whatever the spectral radiance we are getting there, we can from the peak, we can from the equations we can compute the temperature of that body. And mostly in the sensor selections also, whenever we are designing some sensors, okay, we want to study if a body's temperature is spanning from some 100 Kelvin to 200 Kelvin, what could be the wavelength of the sensor, or we have to do for the measuring that radiance, being also be selected based on these equations. Okay. So later I will give some problems. If this could be the temperature, which type of the sensor or detector you want to do, then only you can analyze. If for the case of moon and all, when we are seeing that very low temperatures are there in some part of the regions of moon, we want to see which type of IR detector has to be used to study the temperature of that region. That and all the applications of these equations. You may thinking like that these equations are simply that okay, 1 by t is shifting to this area and all, but when it comes to application level, we find that whenever we know that okay, from the some remote observations how this could be the temperature, so what kind of detectors we can use to understand the spectral radiance of that place, depending upon the peak wavelength is determined by the temperature of that body. So as I mentioned, what is the relevance of, if we are considered, whatever we discussed is about the black body, it is an ideal case. But we know the black body radiations of Earth, if we consider the solar radiation, we know that there is an emission from a sun, emission from the surface, and emission from the atmosphere. So solar radiation, as we know, it is peaking in the 0.5 micrometers, and it get absorbed by, but it is mostly transparent to solar radiation. It is short wavelength to our atmosphere. It is like, but it is vice versa for the surface, Earth surface. So we can see that in the Earth surface, the spectrum, the temperature is slightly less, and we are peaking at that near to 10 micrometer, and we are in the IR region. But in the IR, the most of the emissions, emitted by the surface, it get absorbs and re-emits by the molecules present in the atmosphere. So these, hence, and if we whether all of you have, I think, books. Okay, so shall we do one exercise where we know that if we considered radiative equilibrium conditions, and there is a slab model of Earth where we consider that whatever is the incident radiation falling on the Earth is heating up the Earth surface. So what could be the ardent temperature of the Earth? If I am giving you a solar flux of 241 watt per meter square, and you know the Stefan-Boltzmann law, where we know the temperature of the Earth is, if or any body is this, the flux is proportional to sigma T raised to 4. Yeah. So if the flux is 241, what could be the temperature of that body? You can substitute the Boltzmann constant 5.67 into 10 raised to minus 8 divided with the for solar flux 241, and maybe raised to 1 by 4 is slightly tricky. So it would be around 255 Kelvin, which is how much degrees Celsius? It is given, yeah, minus 18 degrees Celsius. Whether we are experiencing that, no, we are not experiencing that. But if I taking in the case of moon, if the flux is this much, that could be the, but we are taking some other conditions also, because that depending upon the terrain, we have to slightly more, but even then it is directly proportional to the temperatures of the fourth power. So if any body, just like what I want to say example is that if any body, if there is no atmosphere is there, we can use this equation. Because, and it happened also in that when we used this lunar data and all, we have no information of the temperature of that body, but we know from the sun's elevation angle and the position of the sun, we get the flux, and from the flux we are getting the temperature of that region. we are deriving the temperature of this. But in the case of Earth, we have to add the atmosphere. So when we are adding atmosphere, we are finding that the atmosphere can also emit and absorb the radiations. So we can call it as a, but if we are adding only that part, if only the Earth atmosphere adding, we are finding that it gets that calculation you can do independently. So we are finding that it is going too high also, slightly 31 degrees Celsius high where we are taking. So here the concept comes so atmosphere is not really a black body, it's a gray body. So here comes the atmosphere where we find that it is what are for the frequencies atmosphere are opaque, for some of them it is transparent, and based on that we can decide the remote sensing applications. Okay, so this gamma rays, X-rays and UVs are ultimately blocked in the upper atmosphere itself. Visible light we know, which is transmitting and reaching to us, and most of the IR spectrum, if you can see that there is a lot of peaks are there, which are means some of the species are absorbed and by the which is present in the atmosphere. So depending upon that, and you can see that so, and some we can see that in the 10 centimeter to 10 meter around, you can see you can use telescopes because it is radio waves, very large waves which can easily penetrate, and you can study even the cosmic wave or the background that other planets also being studied using this wavelength. So depending upon that wavelength regime, our application and how to observe the atmosphere or the spectrum we can decide. Okay. So in the infrared, if you focus, because most of our species and we are in the atmosphere have the applications in the IR spectroscopy. If you see the different species, O3, H2O, CO2 are the main species which are the greenhouse gases, which we call. So these having the absorption spectrum over this band, where you can see the 18 to 14 micrometer, the transmitter is slightly better, which is we called as an atmospheric window part that we know. So that is the region, and we depending upon this, if you see that H2O, CO2, O3 peak absorption wavelength, we decide in the applications. If we want to study the atmospheric species, we are using those spectral lines to derive if we want to study the CO2 distribution, O3 ozone distribution, H2O. So H2O itself in the IR means which type of transition will be there. In the initial stage, first slide I showed, no? IR means what type of transitions will be there? Vibrational. So vibration kind of. So in the vibration spectroscopy, we study that H2 has a asymmetric stretching, symmetric stretching, those kind of words. So when they are interacting with the IR, it will show transitions at this particular wavelength. So those wavelengths when we are using. So if you now check second time when you are looking into all these satellite wavelengths which they are probing, you can determine by seeing the wavelengths which they are using INSAT and even the SAFI in the microwave megatropics and all. If you see the wavelengths which they are using is particularly for those species, depending upon the transmission lines, they are selecting it for the application. Okay. So these are the atmospheric window part. So 18 to 5, where the absorption of terrestrial thermal radiation by atmospheric gases, there will be little. We can see, but in between small the peaks are also there. So these are the figures showing the atmospheric absorption characteristics with the water vapor shown how the species are there. And in the water vapor, in the case of IR, same it with the microwave also, it has a rotational spectrum also. So it can in the sensitive microwave remote sensing also. So carbon dioxide, oxygen and ozone, methane, nitrogen oxides are shown in the figure. So where we stopped is that when we add the atmosphere also, it is adding up the temperature. So as we know that temperature, it is not really a black body, means whatever it is not absorbing, it is not emitting. Some of the species are also acting in between, and they are also contributing. They are absorbing, re-emitting and all. So here consider the atmosphere as a gray body where we are giving an emissivity absorptivity for the medium. So there comes the Kirchhoff's law. So we know that any body which is a good emitter is a good absorber, which is a poor emitter is a poor absorber. So that is the Kirchhoff's law concept. So all the 4 radiation laws, rather than telling what are the laws, through applications, means how they are Planck's law, how it is determining the radiation, thermal radiations at the particular wavelength, Wien displacement, how with the wavelength the peak shifts, and the Stefan-Boltzmann law, how if a flux we know and the temperature of a body we can determine, or vice versa, if we know the temperature, how the flux determined. And in the case of a gray body, how would be the emissivity and absorptivity of the medium. Okay, so these are the 4 laws that determines how a radiation interacts. Okay, so if we add that part, emissivity and absorptivity part, and for the solar flux, we get the substituting in this equation, we get around 298 Kelvin, which is around 70 degrees Celsius, which we consider as a global mean temperature of the atmosphere. So this is how the atmospheric interactions with the this radiation. So as we know, as the radiation is interacting, it also undergone, we studied absorption, it is taking place, emission. So it is getting extinguished, not by only by absorption alone. There is also scattering phenomena is also there. Okay, so this the reduction of the intensity of the beam due to absorption and scattering in totality is called the extinction coefficient of the medium. So in that we can add it as the absorption coefficient, or the extinction coefficient is the sum of the absorption coefficient and also the scattering coefficient. So we can here apply the Lambert-Beer's law. So Lambert-Beer's law, everybody studied, I think, in your. So when we are considering in the atmospheric cases, when the radiation is transmitting through the medium, it get extinguished, or it get extincted depending upon the absorption and the scattering. So in the case, it is proportional to the path length of the medium through it traverses. If the path length is more, means extinction would be long, and at the same time the concentration of the constituents present in that. So that is called Lambert and Beer's law. The one is path length, another is the concentration of the medium, and the intensity of the wavelength which we are sending. So these 3 independent, path length as well as the concentration and the wavelength, which we are, the 3 parameters are there. So in that 3, because if the wavelength is the intensity which we are sending, it also matters. Okay, so depending upon that, the optical thickness of the, if the optical thickness is high, means it is very opaque, it cannot transmit much, and if it is optically thin medium, it can transmit through the medium. So determined by the Lambert-Beer's law. And when we account this, so this all depending upon the transmittance of the medium. For certain particular wavelength, how it could be. If it is aerosols, haze and all, we are taking the species and all, when it is interacting with those species, there could be a, then that optical depth we call aerosol optical depth and all, which we are using for finding out when we are AOD, we are plotting wherever the dust storms are there, the peaks we are obtaining for, if we are taking the laser this nanometer or this wavelength when we are transmitting, when we are getting peaks, we are telling that the aerosol optical depth is high, then it could be due to this. So that the optical thickness determine the optical the path or the transmitting through. So when we are accounting for all these things, for how much the radiation or the wave get absorbed, emitted, scattered out in, because it is all direction is taking place, then accounting is called the radiator transfer equation. Okay, so it's a simple way we can tell if a intensity, if transmitting through a medium, it get absorbed, means there is a loss is happening. Emission means adding, so it is additional. Scattering out, it is going out, so it is minus, and when it is in, we are calling it as adding up. So it is scattering in and out. So depending upon the wavelength, the species with which it interacts, whether it is depending from the raindrops to big small sizes to cloud interactions, wavelength and all. this radiated transfer equation varies. For the IR, we are using particular set of equations. When microwave regimes are coming, the radiated transfer equations varies. So this is what the basic fundamental things which we are dealing whenever a wave interacts with any medium, lossy medium or lossless medium, or in the example I kept it as an atmosphere. So any medium, it could be through a conductor, through a perfect dielectric. Only thing is that the wave equations won't vary. Only thing is how our applications vary. We decides all these equations. Okay. So these are the fundamental basics what I want to introduce to about the waves. Now I have another presentation. So, it's not moving.
I hope this touchpad is working.
This one you can open too. So if you shall we go to microinverter? Do you have any basic fundamental doubts or something, or whether we can?
Like in polarization, you mentioned that we are focusing on the electric field.
Yes.
Why magnetic field is not?
No, polarization itself is that the definition itself is a locus of the electric field. Yes,
But
its
when
interaction
we
is
like electric field, we are using polarization and we are using
yes, sir.
but why magnetic field is not?
No, magnetic field, whatever we are interacting is that, no, whatever I think this almost in all the equation, if you see, no, the magnetic field, its interaction with, I think, if you see the Maxwell equations and all, it has a Gauss's law and all for magnetic. But when all the interaction with atmosphere and all, no, or not in atmosphere, medium and all, electric field is only dominating. Magnetic field has no much this or other. It will come ferromagnet, ferrimagnetic and all, no, when these are coming. So that time we learned, no, ferromagnet, ferrimagnetic and all. Yeah, there those kind of materials when we are looking into, we are that time, yeah, that magnetic field interaction. So that time I think mostly it is electric field interactions only we are talking about. Air, this like a perfect dielectric. Yes, yes. So this, or we are continuously monotonously speaking, so better anybody can give a slight the nutshell of what I talk, what you understand. Not like that it should be in a sequence way. What you understand from the today's this, what are the waves, how it is interacting.
Like we learned about electromagnetic spectrum, then regarding all the rays, and also we learned about the nature of the rays, like the particle nature and also the wave nature.
Yes.
Then we discussed about the polarization things. Then we discussed about the laws, like the Planck's law, the Wein's displacement law, the Herzog's law, and also
Stefan Boltzmann, yeah, four laws and its how it falls into those applications. Yes. Then
regarding
Lambert-Beer's law, how it is when it is interacting through a medium, it depends upon the three factors: path length, concentration of the atmospheric constituents present, and the wavelength which it is, or the intensity of the wave which it is transmitting through the medium. And we also discussed about that in the case of the equations. Why I didn't go much deeper is that, as we know that equations, that electromagnetic waves, what we were discussing, when it is traversing through the medium at all, no, that depends upon the attenuation constant of the function. It is a function of that one, which is actually depending upon. So it will determine by the penetration depth how a wave can penetrate into the medium. Okay, so now we touch upon, so we talked about all the spectrums varying from gamma ray this to X-rays to radio waves from IR, microwave and all. So focusing on the microwave remote sensing applications. Okay, so where we are talking about 0.3 to 300 gigahertz in the case of frequency, and wavelength, I think meters, centimeter, 1 meter to. So the remote sensing, as we know, the remote sensing, as we know, it's a kind of an eye. It's a technology for this remote sensing, how electromagnetic radiation to where we cannot reach. To using that, we are probing the either it is atmosphere or any this the radiation, and interpret the data from which to extract information about the features and object on the planetary surface or atmosphere if it is remote sensing application. So depending upon the remote sensing, it can be satellite, can be airborne. In the case of ground based also, it can be possible. So if it is in the satellite itself, we know that active and passive sensors are there. Active sensors are there where signals are transmitting and we are receiving the signals. So where I mentioned about earlier. So here come the applications of the which signals we are sending. Horizontal we are sending, vertical we are receiving, or we are sending both, receiving both, and both cross poles or we are receiving, or we are sending cross poles and across circular polarizations or elliptical, this all. So and in the passive sensors where it is measures only the thermal radiations emitted by the body. So as we know in the Planck's law, any body above it will emit the radiations, thermal radiation, any object having a temperature T. So in the airborne, in situ measurements are there, and in the ground based observations are also there. So in the remote sensing itself, whereas if in the extreme left you see the figures, the way how you are observing the atmosphere, if it is high, solar occultation measurements are there. If we are looking other observations we can make, and the limb viewing techniques are there. All depends upon the type of measurements which we want to do. So there are different satellites on the to probe the atmosphere, to probe the surface of the earth using the nether, limb and the solar occultation techniques. If you see the bottommost, it is a scanning by satellite where you can see how the tracks are going and covering the whole, how it is mapping through the surface. And most of you are working in the remote sensing or in the different applications or atmospheric applications only?
No, environmental science.
Environmental. So you are using which type of data sets?
Right now I'm not working with remote sensing.
And not remote sensing, any kind of information you are required for doing the environmental.
I'm actually collecting field samples from
Yeah.
river basins.
River basins, yeah. So you are working some
Analysis.
in the city, going and taking the samples
Yeah.
and measuring.
Yes.
It's okay. So in addition to that, whenever you feel that okay, you have a very limited locations, when you want to explore other parts of the world, you can look into satellite based data
Yes.
also. Yeah. So if we are scanning it in a particular levels, we can see that we can get the snapshots also. The radars are also there. When we are getting the snapshots also, we are receiving. So what are the applications of this remote sensing is to understand the sun, earth, as we know, this climate variability and change, its application, earth and surface. Interiors also, weather is another side, carbon cycle and ecosystems we can study, atmospheric composition, and water and energy cycles. So these are the applications of the remote sensing observations. So as we discussed earlier, so it is the interaction of radiations. Actually, it is now focusing on the microwave radiations. If we are focusing, we know that the microwaves, as we discussed, it is mostly on the molecular vibration, rotational spectroscopy it is mostly dealing with. So due to the permanent molecular and electric and magnetic dipole moment, the water vapor gas molecules, it has a dipole moment which is causing this rotation of these molecules. In oxygen gas molecules, it is a valence electron, so it will contribute the permanent magnetic dipole moment. So hence these two species, this O2 and H2O are sensitive or species which are relevant in the microwave regime. So in the case of the earth, we can see that H2O, O2. In addition to earth also, since it is molecular absorption species, we are not restricting to earth. If these species are present in the, and it is sensitive in the another planets also, we can apply that principles there, probing those Venusian, Mars, and other Titan, Io. So these are the other regions where these other species are also present, where this sub-millimeter, millimeter, again this microwaves are classified into millimeter waves, sub-millimeter waves and all, depending upon the frequencies which they are spanning. So based on the species which we want to study, we can probe the Earth, Venus and the atmosphere of Mars with this millimeter lines which indicated minor constituencies, which are very minor present in the atmospheres, not the major constituencies. So these are the examples of some of the operation or satellite radiometers as well as these are the, if we take the microwave regime, what I told is from 1 gigahertz to 280 gigahertz, we find that the transmittance curve will be like this, where we find that at the 22.25 gigahertz, water vapor has the absorption band, followed by at 60 gigahertz, you can see that's a complete absorption by a strong absorption band. In the 22.5, it is a weak absorption band of a water vapor, but it has been used by the ground-based microwave radiometers for profiling the water vapor. So since it will be a weak, it is for the ground-based application, it will be very sensitive to the water vapors present in the atmosphere. But for the satellite, it won't be. Satellite, we need a strong because it is looking from the top. So satellite, if you take the 183, you find that the water vapor strong absorption bands are there. So in the megatropics and all, Sapphire-like payloads are using 183.1 and different channels, so around plus 11 channels for probing the atmospheric profiles at the different atmospheric level. At the same way, there is a deep peaks and curves are there. So, and the thing is that the window regions where there is species are not absorbing, it is completely transmitting. There, those regions are using for the studying the surface. So hence, depending upon the, if we are using it for profiling the atmosphere, this is classified into sounders. And if we are using it for the surface studies, we are calling it as imagers. So satellites are classified on the basis of that. If we are using the transmitting channels for studying, we are getting the complete surface pictures. Or if we are using much larger wavelength like L-band, this are there, it can penetrate into the surface. So we can get the subsurface characteristics also. So hence in the other planets like Venus, Moon and all, if we are using that, we can know without that remote sensing technique what are the subsurface characteristics of that, whether water is present, whether ice mixtures are present, depending upon the frequency selections. Okay. So what is the advantages of this microwave? As we discussed it can, as due to the longer wavelength, it can provide under cloudy conditions. Day-night observations are possible, stable this and global coverage. As she told, otherwise we have a data if we go one place, in situ observation of that location. But when we want to have a global coverage, there we need the satellite remote sensing. But then the problem is that the resolution will be there. But we can study large scale monitoring. She can study when it is a very data specific to a single location, resolution will be high. We can study the long term variability of that region. So the large scale monitoring could be possible. And main this microwave radiometers are the passive instruments. So whatever the active, what we are calling it as radars, which sending the signals and receiving this. So radiometers are falling in the passive radiometry, means passive remote sensing technique, and where we are using it for studying the precipitations using the TMIs and all. Then sea ice is possible, sea surface salinity if we are taking the surface, this ocean surface wind we can study. And if we are taking the temperature profiling, if it O2 sensitive channels, we can derive the atmospheric temperature profiles. Since it is sounders, multiple wavelength will be there, and hence we can probe the different layers of the atmosphere. So we get the temperature profiles, and if we are using water vapor channels, we can derive the humidity, and if it is cloud sensitive, we can derive the cloud characteristics also. So depending upon the applications, the bands can be divided: L band, S band, C band, X band, KU, Ka band, millimeter and submillimeter waves. So this L band we are using for 1 to 3 gigahertz for soil moisture, because as we know, it has a longer wavelength, so it can penetrate deeper. So, and sea surface salinity also using this. So ocean surface wind and all, we are using this 1922 gigahertz, which are the window channels, which is not being absorbed by any of the species. So this can be used for studying the surface winds and all. So sea ice. Then atmospheric temperature we know from the oxygen absorption band we are using. Oxygen, why we are selecting oxygen? Oxygen, not like other species, it is uniformly in a homogeneous media. So whatever emission is coming, it is due to the variation of the temperature. So hence the oxygen spectra is used for deriving the atmospheric temperature profiles. So it also has a band in 118 gigahertz. And for the precipitation, we are using the window channels like 11, 31, 37 and 89 gigahertz. And the water vapor, liquid water and all we are using. And for the stratosphere study, the planetary atmosphere, where as we mentioned, the minor constituencies are present, the submillimeter waves can be used, but there it should not be get affected. If the lower atmosphere is high pressure, high density molecules are present, so there if the waves should not get, we are using limb viewing techniques, okay, for studying the minor constituents. There it is actually, if it looks like this, limb is looking through this, so it will directly transmitting to the lower atmosphere. So whatever we are looking, we can study the minor constituent through that viewing observations. So the other planets also same way, if we want to study any such species, we can use these frequencies. So as I mentioned, the remote sensing is divided into active and passive. Active, where there is a signal is transmitting and receiving back, and whereas the radiometer, it measures only the brightness temperature. So we know the whatever it is transmitting a radiation, the receiving back, it will depending upon the wavelength, the cross section from where the signal is coming back, the gain of the antenna and the radius it is measuring. So it is using its own source, receive backscattered microwave energy, depends on surface scattering, and hence it is also depending upon the target, the signals varies. So if it is the roughness, it is, and it also depend upon the surface characteristics and also the system parameter that is coming in the subsequent slides. What are the system parameters? Means which wavelength, which angle we are looking into, and what type of the target you are measuring. Okay, so depending upon that, there are scatterometers, altimeters, radars, all are using the active principle for measuring the techniques, and it has a high resolutions. Okay, 10 meter. Whereas the passive is using emission from target in the source, receives this emitted energy, and hence depends on the emissivity of the medium, emissivity of the body or the surface where we are measuring, and the temperature. And it is less affected by the surface roughness or vegetation or whatever the medium it is traversing through, but the resolution will be poor. So as we discussed earlier, the Planck's body radiation law, where the equation is like this, but since we are falling in the millimeter wave, that means that the longer wavelength region, we can reduce this Planck's body to Rayleigh jeans approximation. Actually, both of their this is that. So that's what I told. All these radiative transfers get modified according to the spectrum which we are looking into. If we are looking into the IR thing and all, we have to take the Planck function as level. But it is in the longer wavelength region, we are reducing it into Rayleigh-Jeans approximation. Okay. So this Rayleigh-Jeans approximation advantage is that here the whatever the radiation emitting is directly proportional to the temperature or the brightness temperature of that body. Okay, the brightness temperature is this one. If you can see that the brightness temperature equation is that if the at a particular wavelength, we are equating that equation, no, the Planck's equation, to a higher wavelength, we are approximating the denominator to very less than 1, and hence the whatever the brightness temperature we are measuring is proportional to the temperature of that body. So then if we take the same temperature, what could be the physical temperature? That ratio we are taking, we are getting the emissivity of the that body. If it is a completely black body, the emissivity equal to 1 means the brightness temperature and physical temperature will be the same. Okay, but it is not the scenario. Emissivity will be always less than 1 for any medium. So that difference is called the physical temperature and the brightness temperature. This will come. So this related that brightness temperature or the emission from a body. So in the microwave, whatever we are measuring in the passive microwave radiometer is proportional to the temperature of the body. It is expressed in term of the brightness temperature. So it is called brightness temperature. So it is also related how energy is radiated from physical media in comparison to a perfect black body. So we are using the term brightness temperature. So if you take next time, whatever the radiometric observations for your analysis, whatever the level 0 data will be your brightness temperatures. Okay. So and I told you it is the, if it is a perfect black body, the emissivity will be the 1, then the physical temperature black body, brightness temperature will be 1, but it is not the scenario. So emissivity here plays a significant role. So emissivity is the function of this frequency, the polarizations which we are discussing earlier, and the direction of the angle in which we are observing the surface, and dielectric properties of the medium and other properties of the medium which we are coming into. Okay, so if you see, this is an example of electromagnetic wave. The right side of the wave, we can see that the emissivity, how it varies for a dry soil and a wet soil. I gave an example. Okay, EV and EH. Understood? No, in the preliminary slides we told about the vertical polarizations, horizontal polarizations, how it interacts with the medium. V means it will be perpendicular to the angle of incidence medium, so it will be less interacting with the surface. Horizontal polarization means it is parallel to the surface, it is interacting much with the surface. So if we are taking emissivity, we are computing. So this is what the with the incident viewing angle, how the dry soil, the emissivity will be the high. Wet soil, you can see the emissivity is slightly lesser because due to the dielectric constant. That also we mentioned how the waves when interacting, dielectric constant plays a significant role in determining how the waves are penetrating into the medium or not into the medium. Okay, so emissivity decreases with increasing the dielectric constant. So dry soil means the dielectric constant will be less, but when the wet soil comes, the water part is adding into that, so the dielectric constant varies. So it will changes the dielectric. So and in the water bodies, the emissivity will be 0.5. So depending upon this emissivity values, we can do the surface characterizations. Okay. And this viewing angle is also very significant. If you see where this EV and EH maximum difference is occurring, mostly those incident angle is used by the satellite for studying surface characteristics. Then only that's I told about Brewster's angle and all, where you see that vertical transmitted and horizontal will be the reflected back. So there the difference will come. So depending upon that, the satellite incident angle will be determined. If you are viewing at the 40 to 50 degree, if you see the satellites like whatever you are using for surface studies, the incident angle would be between that. And again, there's a compromise between the our electronics and availability antenna, this will be there, but it could be there. Then only the vertical and horizontal difference will be maximum. Then only we will get receive the signals back from the and we can differentiate the features of the surface. So that using that we are identifying the vegetation types, characterizing the surface based on the flood, drought, whether it has happened and all by this sending. So horizontal, vertical signals why we are sending, at what angle we are viewing, that difference how the emissive nature of the surface varies with this angle of incidence. Okay. To the okay. Okay. And it is what about not only related to, we can restrict to earth also. Now we are moving planetary explorations and all, no, so there also it has a lot of immense applications, this radar observations or this radiometric observation we are taking, this emissivity, because this dielectric part only they are using in the other planets also to decide whether there is a water ice presence or what I told earlier, because this dielectric huge difference is there in the dry soil, because most of the moon and all, no, it is basaltic regions and all, so there the dielectric will be very low and it is specific value will be there. So whenever there is a change in this dielectric is observed, they are identifying those regions as the regions where there is a possibility of the water ice and all. So, how to ask them? So anybody can then brief on what is the emissivity or the what is emissivity? First, let's start with a small question. What is the emissivity of any medium? Anybody else can now try? You can attempt. You are doing research in which field? Remote sensing only, yeah. So anyway, you are already on which applications you are on? Slightly louder. River basin. So you are using which? Sentinel. Oh, very good. Okay. Sentinel. EOS4. List. IR. List 4. Okay. 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 Then why you selected Sentinel? Then my question is that. Which band Sentinel is using? No. No. Which was Sentinel 1 you are using or Sentinel 2? 2. Okay. Okay. Then Sentinel 2A. Okay. Okay. Sentinel 1 whether have you used? No. Sentinel 1 is using C band. So where we studied now, no, L band, C band, okay. So C band is using for the surface studies. And I think Sentinel 2A you are using. 2A, okay. That is for IR. Okay. For then why you selected that one? Then that could be the question. That is even at IR remote sensing, you can answer that one.
Land use and economic, I use Sentinel 2A, but Sentinel 2A resolution 10 meters and list 4 resolution 5.8 meters. Now I use list 4.
Yes, sir. Why? It's not like that. Why you selected those data? You have some objective in your mind, no? Why you used this whatever land cover and land use? Why you are particular about this Sentinel 2A? Or since Sentinel is giving land use, you are using not like that, no. High resolution data, yeah. Okay, it's a scientific. Some reason should be there, no? Means what is the objective of the Sentinel? How it gives how it gives a land use or land which parameter it gives? That's what precisely question.
Band, visual infrared band I use for signature.
Which parameter it gives? From where you are using land use? First, you before plotting, you are using some parameter, no? you're not giving any parameter. For example, what I told, no, in the case of radiometers, it is giving level 0 brightness, temperature will be giving, and from that we are deriving a water vapor profile or this profile, or anyway, what parameter you are using to confine that, okay, this is a land use, this much area it has been used or it has not used. How you determine which parameter you are plotting? Surface reflectance value. Yes. So how that surface reflectance is what? Means whether it is active. What I'm mentioning.
Very less reflection,
Mm.
0 or minus, and vegetation there high reflection, 0.5 to
Yes, yes. So NDVI you are computing.
all indices.
Normalized vegetation index you are computing, and that based on that you are determining. That is what my question is. Okay. Since it is really available, don't tell like that. Your purpose is that you are using the reflectance value to determine whether it is a land use. So that is the. So that reflectance you are getting. That reflectance you are getting from where? This sentinel is whatever you are using, an active or passive. Okay, so whether they are giving the reflectance value to you, you are using those values to decide whether computing some certain parameters. Based on that, you are deciding that it is a water settlement and all. Yes. So that depends upon that values. No, so you are using surface reflectance values. So I have to tell like that. So you have given. So I have to distribute some chocolates to you. So. Then somebody else, here nobody's looking at me also, thinking like that I will answer. Background, no problem. It's only basics I'm taking. I think you are aware of this waves. Okay. You are avoiding maybe. For your oceanography application, most of the things I think you are removing atmosphere, no? Yeah. Yeah, no problem. No problem. You are able to this, no? Understand? We are getting. No, that is not required because those. That's why I told it. If I want to definitions, no, I would have put a definition, so that would have been easy. Rather than putting definitions, how it is applicable in different scenarios. That's why I want to just do this.
Suppose sea surface height or something, which we used to get to some site. ESSO and
yeah.
But rather than that,
Scatterometers are giving no sea surface height, huh? Bracks. Okay, you just ask.
And my doubt is, suppose specific things like coming to ocean waves, that direction, direction of wave, and even wave height period. Those type of things we want to get. Altimeters.
Altimeters are Altica and all, no? Whether you have used it, no. Nothing.
Because freely available ESSO only, as of now I found.
Yeah, that is what type of data?
ESSO means it used to give NC format, that's sea surface height.
Directly they are giving sea surface height.
Gridded format. But rest of them are paid or something like that.
No, that you are not. That and all are other part of this. No, what I asked is why there is any purpose. No, why we are selecting. As she told, no, it is not freely. That's we want some science data. No, so we want surface reflectance. Same way you are directly using sea height, sea surface height. Okay.
Some other sites are there where we can directly get reanalysis data.
Okay.
Since that's available,
you have to directly using that. Okay.
But this remote sensing things I didn't use.
No, remote sensing. Maybe this data, whatever you are telling, is a product of.
They are
in that. The data we use,
all are this remote sensing observation and the modeling data only. Reanalysis are all the combination of that. Yeah. So what is my point is that no, when you are using any data, you use it. But first of all, you understand how that data came also, because we are readily getting sea surface that we are using, but that may be level 2 data. Before that, one level 0 will be there. As she told, surface reflectance we are getting same way. If it is in the case of, I think, scatterometers or altimeters which they are giving, I think they are taking this waves when we are taking the Bragg's reflect. We studied, n lambda design. They are taking that wave transmitting through the waves, and that equations they are using to derive this surface height. That will be the parameter. But you use that to understand, for your understanding, how you are getting that sea surface height. You are using product, but you understand how you got that variable. Okay, then you will understand that that application, which frequency they are using for this. Which frequency maybe they are using? Any idea? No idea. Okay. And which any sat, it is not satellite. You are using your reanalysis data. You are directly getting sea surface height. Okay. And what is your application?
Sea surface height anomaly. It's not the height. It's anomaly. Sea surface height anomaly.
Actually, from ERA5 data, is whatever wave parameter I can directly get rather than sea surface height.
Example?
Significant wave or wave period, wave direction directly I am getting
from ERA.
That is an output of wave model plus
okay.
This whatever available observations with satellite.
Okay. Yes. And eventually, what you are finding out? The sea surface height from the height. What
characteristics of that particular region, wave climate of that particular region.
You are focusing on which region? Any particular region you are focusing, or?
Arabian Sea.
Okay. So in the I think in the Arabian Sea. Okay. Then it is global coverage, that's why big coverage, big domain it is, yeah. Then point observations. So anyway, you have to use then this satellite data only, and you see that how they are deriving those parameters. Anyway, this altimeters and all are using this Altica and all, which is ISRO, this Saral Altica and all. They are deriving. No, as you that is availability second one. What that may be, whatever reanalysis may be going into that. What I told is that how they are giving those data. Okay, you are looking into those aspects and which parameters and all for your better this understanding and.
So this Altica is also included.
Yeah, Altica is included, I think. And I think frequencies are also that high wavelength regions are there. I think ocean sea surface roughness and all they are studying. Sea surface roughness and which side is rough, and the roughness they are connecting to the monsoonal activities also, means whether sea is very rough and all those kinds of studies are also they are connecting it with the.
Suppose I want to, as you said, sea surface roughness. So some person I want to study, then through this satellite observation, then the possibilities, will you please explain like how one can do sea surface roughness using satellite observation?
And actually sea surface roughness they are providing, I think, they are level 2 data. As I told, this scatterometer, Sentinel is not giving. I think for that you have to go for scatterometers. Certain higher wavelength is required. I think it is whatever Sentinels are using, not like that IR, that are using C band. So wavelength is around 5.6 gigahertz and all for Sentinel. They are using the surface characteristics and all soil moisture studies, whether sea ice presence and some deformations in the lands happening, landslides and all. For that purpose, they are using the Sentinel data, depending upon our applications. But for the, I think, ocean surface roughness and scatterometers are used. Their applications are scattering part is also different. The waves are coming and all, and they are deriving surface roughness out of that. So you are getting surface roughness. If you want to study, I think you have to detail that derivations are there. What I understood is that they are using Bragg's law for that each waves are when interacting with each waves surfaces, they are using how much the wave transmitted back, the distance they are taking, that traveled time they are taking, and from that they are deriving the surface roughness. Okay. So that level you can use it in the second. And what about you? You are working on a
Working as field test.
eh?
Field test.
Okay.
So gathering information from the
Field. On which parameter?
field. This boy data. Then
Wind and okay. And ultimately what you are studying and then
Actually, my job is to gather this
okay, collection of data.
want to how the process and
Okay.
also this remote sensing what just want to explore this.
Okay. Remote you have to declare. What about you? You are expert in your name. Could you please tell her? Ocean, yeah. Oceanography, yeah. Or ocean. So you have any plan to use ESSO and all that upcoming missions were there, no? No. ESSO, NASA, ISRO, SAR, this is there, no? Yeah. So I hope then all are from different background. Yeah, good only because we also learn in that process and scatter. Because I am mostly working on the surface of the now focusing on the lunar surface and all. So I am in the surface Earth surface and all, where we seen that in the scatterometers which we used for the surface terrain characterization. So we have seen that it is being used also for the ocean characterization study, surface roughness and also particular aim is that only. Okay, so you can explore some of the how and you can read how they are using those. You can get the data available, but how they are probing it and how you are getting that data from the reflectivity values or from the scattered back signals, how they are deriving the surface roughness and all. So now we have to that passive microwave remote sensing what we are talking about. So slightly we're looking into the atmospheric. She's so close to you see. So I told no the whatever in the case of IR and all the radiance is the whatever the level 0 measurements what the satellite is measured. So here we are representing it in the terms of the brightness temperature. So whatever the brightness temperature reaching the satellite will be the combinations of so many. So whatever we are getting that level 0 or whatever values, it will be the combination of reflections from the surface, from the atmosphere, and also we have the radiative transfer equation which I mentioned in the preliminary slide is very much important to know that which part is contributing which part. Then only we can segregate it and we can get an actual real parameters. So that part is called the retrieval part. Okay, so that is the retrieval part is involved where we are retrieving the parameters what she mentioned. No, we are getting the ocean roughness straight away, but it is not the straight away. So whatever they are measuring from the radiance or from the brightness temperature, we are doing a retrieval process and then we are deriving the parameters which we want. So any observations have a retrieval procedures. So there are different types of retrievals are there. Now even at AI techniques being also been used for the retrieval purposes and all. So if we are taking the basis, the Bayesian variational retrieval techniques are there for the brightness temperature what it measured or the radiance what it measured. From that, the upwelling radiation part, the downwelling radiation part, how much it got attenuated while it transmitting through the atmosphere, all this accounting is needed for deriving a parameter. So it is like an inversion technique because we have a brightness temperature. We want in that the parameter is there, but we have to do all the mathematical calculations or this. For that we need a priori information. Means if this could be the profile, this could be the brightness temperature, or this could be the radiance. So that a priori information should be there to train the model. That is what AI is also using. So it's like a lookup table, or we can train the model is required to derive this atmospheric parameters. So whatever the values we are telling, what we have to derive from the radiance values, we need processes like this. Okay, so for that first we need a background data is written, which is called a priori data. For this could be this. So now we are making the mathematical equation, train it in such a way that when we get a new brightness temperature and when we are applying this retrieval procedures, we are getting the temperature profile retrieved like this parameter, the water vapor profile will be like this. Okay, so and this the right extreme showing that why we are using the multiple channels are also using. If I think even in Sentinel, I think surface data except images where they are using a single channel. All the sounders are using multiple channels, because for the multiple channels are probing the different height levels of the atmosphere. It will be sensitive to the different height levels. So then only we can do the profiling of the atmosphere. So in the case of the ground based microwave radiometers or the up look or the down looking radiometers, they are traversing multiple channels, are sensitive to the different layers. If we are using the central band of the frequency, it will be the most sensitive to the species, so it will respond where the maximum species is there. The remaining, the rest of the channels will penetrate much deeper into the atmosphere and get the information beneath the layers. And in the case of ground based, it will be vice versa. It will be exponential. Maximum will be the down. As we go, the species will be less and we get the less number of informations. So these are the weighting functions we are calling. So the weighting function will give us how sensitive is each layer to each radiances. So based on that, first we derive the weighting functions, and weighting functions will be act as a one of the parameter for the retrieval purposes. So this will be fed to the radiances what we observed, and then we are deriving the profiles. And the profiles derived is shown in the bottommost panel, the Neelam cyclone, where you can see that how the brightness temperature itself varying when the cyclone is formed over this regions. So you can see that these are whatever I shown is that how the multiple channels means the even in the single satellite itself, the certain payloads depending upon the applications, it can do cross track, across track, whatever, and the angle of looking, all depending upon the applications of the surface which we want to study. Okay. It is an example of the ground-based microwave radiometer, which is over our VSSC. It was there. So it operates at the whatever frequencies which we discussed, 22.23 gigahertz for the water vapor channel. It is a slightly absorption peak there, a weak absorption channel, but it is being used for the water vapor channel deriving. And then the 60 gigahertz oxygen channels are there, which is using for temperature profile derive. So these are the two major channels being used. Since it is in the ground based, here the radiative transfer, whatever we are taking, it will be contributed by the downwelling radiation, and the sum will be. That's why I told the radiative transfer equation slightly get modified. It is now there is no upwelling part we have to do. Only we have to look into downwelling part of the radiations. So from the brightness temperature, what we get is the absorption coefficient information we have. Now the weighting function we derive how the each wavelength is sensitive to the each at the each height of the this one, and then we are using the normalized weighting function for the feeding into that inversion process, and from the brightness temperature with all the absorption coefficient informations and the weighting for informations, we are inverting the profiles. If you see the water vapor density profiles and the relative humidity profiles which we derived are combined with the radiosonde profiles. So with this we are doing the validation purposes. And the left hand figure shows the temporal evolution of a system during the different scenarios where the humidity was specific humidity is shown in the this one. It is during the monsoon time, how specific humidity at the different levels varying and how it is distributed. And the bottommost panel is showing the relative humidity variability during the convective and big rain event occurred over the region, and where there can see that how the humidity is accumulating and resulting in the deep convective rain for a continuous period and followed by stratiform. There you can clearly see how the cloud patterns and all are varying. So these are all the derived parameters from the brightness temperature what we observed. Okay. So this is about the ground based. So now what I mentioned is about the from the space, how the this radiometric applications for measuring the soil moistures and all. So what we mentioned is that there are soil moisture active passive missions where there is map and all, which they are using this radio this I think active and passive both was there, means they simultaneously measured active part and also the passive. These are they some baseline models. So there, as I mentioned earlier, this the dielectric property of the medium is mainly used by these applications for measuring the soil moistures. And these wavelengths are also, I think, L band and all they are using for the lesser atmospheric attenuation and larger penetration through vegetation should be there, because if it is a C band and also why this Sentinel-1 and Sentinel-2 is also the same application, because Sentinel-1 is also being affected by the vegetations because it is C band, it is not penetrating much, but is so in order to so see how the surface reflectance and vegetation part is affecting in Sentinel-2 they are adding IR part, and from that they are computing the NDVI, normalized vegetation index, to see wherever the vegetations are high from the ratios and all, and they're delineating that part and seeing that from where the soil moisture or surface part is contributing and but which is part by the vegetation part is contributing. So these are all the based on the how these brightness temperatures from the different layers we are computing the soil moisture, and inverted or the derived retrieved soil moisture is shown in the panel. This is how the soil moisture is mapped over the region is shown. So what we are discussing so far is the radiometric applications. In the active microwave remote sensing, as we discussed earlier, it is transmitting signal and the same day it's received back also the signals. So in the X band, if we are using the problem is it is affected by the vegetations. As you see that we are getting the reflected back signals will be the contribution from the vegetations from the vegetation mostly. If we are using L band, it will be slightly more penetrating and in the barren land and all we can use these kinds of bands, but in the vegetative part we have to be very we have to delineate it with the, as I mentioned, the vegetation index also we have to compute, and we have to remove that vegetation part, how much contributing and how much from the surface part. The below is shown it is a barren. If it is not much affected, much vegetation is there, we can see that L band can then penetrated much deeper below some 2 to 3 centimeter, and then we can get the subsurface features also. So depending upon the surface terrain, so this whatever the active radars or active sensors are measuring the backscattering coefficients. So this backscattering coefficient is a function of the surface roughness also, and as well as the system parameters. What a system parameter mean is that incident angle, the polarization it which measures, and the wavelength we are using, that are the system parameters. So it is function of these three parameters. In addition to that, it is also the function of the surface characteristics also, means whether the surface is smooth or surface is rough. So surface roughness is again determined by the some H factors are there which we are computing to determine that how rough is it is. Something if it is roughness itself is having different criterions. So based on Fraunhofer criterions and all, we are dividing it into whether it is smooth, rough, or extent of roughness also. So that is also, so this backscattering coefficient, even though it is a single parameter, it is a function of polarization, wavelength, incidence angle. In the case of system parameters, in the case of the surface parameters, it is a function of roughness and the type of the terrain which we are looking into. So hence we have to have a involved retrieval procedures to get the back the, so if we want a soil moisture, we have to derive from the backscattering coefficients. So and as I told, that's radiometers, when we have that resolution, this is there. So synthetic aperture radars means SAR, what we are discussing now, the radars are using multiple this aperture sizes, that whatever it is traveling through the path, they are combining that small apertures and making it into a bigger elongated aperture. So the aperture size is high means we are getting a high resolution data. If the aperture size is very small means, so but if we, due to the limitation of our this we cannot go with the very high aperture size, we have a limitation of that. So what we are synthetically aperturing it. That's why that name is come. I think that is what's slightly familiar URL. That's why everybody is very happy with that word. So there comes the synthetic aperture radar. So it will give a high resolution data. So in the recently we have our NISR mission, NASA ISRO synthetic aperture radar, where we have a L band and S band. L band is using 1.25 24 centimeter, which can have a much deeper penetrations and all. So before that launch itself, there is a thorough validations has been done, because then only I told because it's from deriving the sigma. Deriving the soil moisture is a very involved, because it is a multi-dependent parameter, multi-parameter function. So when that multi-dependent, when function is a lot of function of a multi-parameters, when we have to retrieve that soil moisture from the sigma, it's a involved process like that any other parameters also. So this NISR with an objective of to study this, since it is a combination of L band and S band, it is for first time that combination is coming. So whatever is what we have seen in the X band, L band, whatever vegetations, combinations, contributions, L band vegetation plus surface contributions are coming, S band falls in between. So whatever correction or whatever contributions are there, we can find out whether. So it is expected to get a high resolution observations with the high accuracy we are expecting from the NISR observations.
I have a question.
Yeah.
Like, so here you said a small aperture is lower resolution, whereas a larger aperture is higher resolution data. So you're saying that to increase the aperture, we are using, so how is this synthetic aperture? Like, how are we increasing the resolution?
Yeah, that they are combining, as you see. I think she can give better on that one. She's very happy when I talked about synthetic aperture radar. How with that aperture they are combining? Because the big antenna resolution equation is that. It is not mathematical modeling is not coming now. First they are that multiple instant. Yeah.
They will be calculating like using some equations and all, they will be calculating how much it is taking it, how much the reflections the brightness temperature is taking it, and then they will look into the angles also. Like there are different angles, like how it is distinguishing each features. Then they will be like making those smaller apertures into a long.
Actually, if you can see that in the figure, this is if it is a one single aperture, that small one, the resolution will be the bigger one. If you see that aperture, small one, center one, if you see, the aperture is this much high resolution, 2 kilometer resolution if it is, for example, if it is at a 400 kilometer altitude. If that single aperture, you are moving in a moving platform, if you are combining that each apertures, and then if you are taking the whole length, it become 2 kilometer. Then the resolution is reduced to 1 by, I think half of that aperture size it become. So they are combining those each segments and synthetically aperturing. It is not real one. That's why that name they coined it. It is synthetically apertured. It is not real one. Actually, they are combining that each apertures and considering it as a single one to get a maximum. This one is. Am I right, or you want to add something? I think she can add something.
So each aperture length is 8
Real
meter.
aperture, their length is 8 meter.
Hmm.
And we'll add all apertures with the aperture is 2 kilometer.
No, how they are combining that each apertures or how they are not, we cannot tell. Okay.
But like if we need high resolution, then we need to keep a very long antenna in the satellite. That is the like the practical. But it is
That
not
lambda by d
possible.
equation is there.
Lambda by D.
Resolution is proportional lambda by d. Okay.
Then
Then
we can't keep that long antenna
And
on
in
a
a
satellite
satellite.
and we can't keep it there. So we virtually keeping those small apertures and we are like
we are synthesizing it into that consider that each observation and synthesizing it into considering it a bigger aperture, and then we are taking reducing the this one. As she told us, some equations are involved into that, and we are how to synthesize it, how long it should be considered. All these are determined by that.
So you mentioned that each aperture size is 8 meter. When we will take the data resolution will be 8 meter.
Each
no 4 meters.
it becomes 1/2. That is the advantage of the synthetic aperture. Whatever was the aperture, the resolution will be very high. It will be the half of the aperture size.
No, so complete aperture size is 2 kilometer.
Yes. Individually, if you take, it is only 8 meter. Yeah. For 8 meter aperture size, the resolution was very high, around 2 kilometer. Yes. And when you combined it and made it into 2 kilometer resolution, it become 4 meter. That means it's the direct principle is that whatever was the whatever is the aperture size of a single antenna, half will be the resolution. Means 8 meter aperture size resolution will be 4 meter. The combined it is such a way that. Okay, the principle is that is not depending upon the altitude. Mostly in the radars, the aperture, this is depending upon the altitude at which it flies and the wavelength and all. That equation is lambda r by L. But in the case of synthetic aperture, it is straight away aperture divided by 2. It will get that much, we can gain that much resolution. So it is some basics on the how the radar equations gives the backscattered power received by the radar is actually the transmitted and the received. It is a function of the wavelength, and also the backscattering coefficient is sigma 0. It depends upon the gain of the antenna, and the A is the area of the antenna. And as I mentioned, this SAR data, it has application for disasters like for studying the flood, the cyclone, whatever in the surface characteristic variability we can identify using SAR. So submerged vegetations where they are taking now whenever this cyclones and floods are happening, they are showing SAR images of the previous and after the event. So we can clearly demarcate whenever wherever the dielectric, whatever water is flown into in Wayanad case and all, they are showing in the SAR images and all, wherever the dielectric varied, that part and all is evident from the surface maps and all. So then land deformations, they are taking INSARs and interferometric SAR observations for getting the land deformations happened and all. Then oil spill monitoring. That's why I told in the oceans also they are applying it. Okay, in ocean parts and all. Glacier, lake hazards, volcanic eruptions parts and all they are using. So as I mentioned, the radar observation parameters, frequency, polarizations in which we are sending the signal, horizontal signals we are sending, we are receiving back whether vertical, HV combination, polarimetric radars and all HV combinations are using. H is transmitting, B is receiving, and the combinations of they are using to understand the surface. Based on that, they are dividing it into volume scattering, if it is from the surface, or double bounce scattering if big buildings are there. All this has to be known, then only we can segregate from the backscattering coefficient which is contributing which part. So, and in the surface, the backscattering coefficient determined by the roughness, viewing geometry, and the dielectric properties of the medium. So whatever I mentioned, this is look like the SMAP radar mosaic in the Amazon basics is shown in the left, the topmost figure, where we can see that in the where are the water basins and all the very black places, we can see the water basins are there. Then depending upon the volume scattering part, we can decide the how much is the vegetation part is contributed by. If it is double bounce means the buildings or big this is there, then specular reflections are there, where the smooth surfaces are there, and based on the rough, the backscattering coefficient will be different. So from the backscattering coefficient and the combinations of this one, we can clearly demarcate what type of surface it is there, whether the river basins are there or where the vegetation parts are there. That I think that high white colors are all demarcated by the in the Amazon basic vegetation part contributions are there. Or in the and the radar altimetry which we are discussing, for the oceanography, river discharge, reservoir volume, which can be used for calibration, HH. Horizontal to horizontal curves we can use to generate this. So they are used by the Altica, Saral Altica and all. No, these are the Ka-band 35.75 gigahertz mission with the highest sampling rate of 40 hertz we are using for studying the hydrological parameters. As I mentioned, INSAR applications are like for land deformations, how they are like that signals they are sending. Several types of combination interferometric SAR observations are there. There we are transmitting the waves and looking into the aspects, and they are. So these are just glimpses of what are the radar applications we can use for this. And in the planetary surfaces also, these radars are extensively using. Actually, in the L band, we have dual frequencies in the thick aperture radars are there. So depending upon the craters, whether that craters are the freshly made craters, actually the life of how it is made, whether recently only they made, depending upon the this actually this combinations, no, this L band DSR, I think horizontal vertical polarizations they are using, and the get back signals from the ratios they are deriving so many decompositions they are doing, decomposition, polys decompositions and all. Based on that, they are finding out some fractions and deciding whether these craters are fresh craters, and some craters are the anomalous in which is a polar nature, whether water content present or not. So they are in the lunar also, they are differentiate, means surface studies they are using in the polar lands and all. This here in DFSR also, both L and S band is there. This is actually shown by the L band regions. And in the Venus surface also, if you can see that Magellan, this observations, from the data we can see that the volcanisms occurrence of this are present in the. So it has an application not only in the Earth surface but also in the planetary surfaces also. So these are the microwave applications. First we studied what are the basic microwave. We are looking into all the radiometers and radars and all, and how they are applied to understand the surface features. So these are the basics of the microwave remote sensing. So if you have any doubts, you can free to ask me.
Ma'am, can you suggest how can we apply remote sensing when it comes to environmental degradation?
Environmental degradation. What degradation? Environmental means which parameter? Could you please be specific? Environmental degradation in the sense can be drought, flood, or something.
Chemistry point of view.
Okay. Means if you are burning something and no.
Metal contamination and all.
Metal.
Chemistry, chemical aspects.
Okay. No. Eventually, it will affect what? I mean, metal contamination happened. Our health.
Biodiversity, health.
And maybe you have to do, but that maybe you have to know the reactions and all, no?
That remote vegetation health we can check. Like if it is healthy means like the brighter will be the vegetation, and then if the vegetation health is deteriorating means that if stresses for the vegetation, then there will be something.
Okay.
And observation.
The health of the vegetation can be it can be measured. Health of the only thing is that the vegetation, how green.
Can deviate, then we check whether it is like brighter,
Ah,
or like if
if
there
there
is
is
any
a,
stress, then the like
but
the
it
brightness
should be, I think, slightly bigger
Ah.
area, then it could be okay, because in cultivation areas they are doing like that, some deformations. I mean, so some, this has happened from the in DBIs and all, they are doing. But I think for your thing, I feel like that it is slightly chemical reactions are also involved in that, no? This one. Otherwise, if you environmental degradation, the point of view, if something burning you are, or you are doing, then forest fires, we can look into those aspects. And also the aerosols also, if some kind of species are this into the air, emitting into the air, and means is present in the air. If you burn something, if that concentration is increasing, keep on in area something is increasing, then we are, if air quality we are checking, we can understand that, oh, how much air constituencies have been changed compared to the previous. When we're breathing air quality, I think air quality observations are
We can stop now that
okay.
sharing end the session, online session.
This is actually, this didn't work. Yeah, you can. Yeah.
Postpay is not working.
ചെയ്യണോ? വെറുതെ
Alt control.
Alt control.